Okay, maybe ready?
Yes.
All right, it's a great pleasure and honor to introduce Professor Artur Avila, 2014 Fields Medalist from University of Zurich and Impact.
Yes.
And he is a recipient of the Frontier of Science Award 2024 in Dynamical Systems and Ergodic Theory. He will be telling us about his work. This is deterministic delocalization.
Yes.
Okay, please welcome.
Thank you. I hope I can you can understand me. I have a little restriction because a little bit of sinusitis, so I cannot speak very loud. Let's see if I can be comprehended. So that most of this work is a joint work with David Damanik, but there is going to be a new paper also with my student Andrea Uliana. Well, there's no paper available anyway, but that's what it is about. So the general thing that I'd like to try to understand in this talk is some matrices that are large. So there is a matrix here, and then it's large, has some big size, of some special types. And I'm going to be interested on the eigenvalues and eigenfunctions of this matrix. This is a topic that's sometimes studied from the point of view of randomness. You consider probability, you consider random entries of a certain type, and then you'd say interesting things about the typical distribution of the distribution of those quantities. It's not written but was mentioned, the topic is deterministic. So though we can say things about everything, it's not, the focus is not on the randomness. And we work with a very special kind of matrices. So you could look at self-adjoint matrices, you could look at the unitary matrix, and so on. Here they will be self-adjoint of a very specific type, because I'm interested in operators that from matrices that arise from the Schrödinger equation on a lattice. So let us, or on a box. So consider n is just the integer like this. And on this, so you have some dimension bigger or equal to 1, and then our space will be this. It's also possible to, most people work on infinite limits of this. In this case, you work, the space would be ZD. This you can think as a limit. It plays a role in this talk, but I'm mostly concerned with finite box case. So n to the d is our space. And what's the kind of operator that we're interested in? So it's a Schrödinger operator. It's H. It acts on L2 of this space. And it takes unit a vector. So then the nth coordinate, after you apply the operator, it applies so it does. So this is a discrete Laplacian on this space, plus a potential here that acts the diagonal interaction that depends on a potential. So u n. So this is the Schrödinger operator. It depends on a function from here to, so a real function, which could be also defined on ZT. I'll be always talking about uniformly bounded functions. My interest, if it was in ZD, it should be just bounded, but here I'm thinking as n goes to infinity, and if I concentrate on the case that everything stays uniformly bounded. So usually, maybe let us think that there is a parameter, a lambda bigger than 0, some size, and then it takes values on some bounded interval. So there will be always this parameter that's supposed to be fixed, and thus everything might change. Okay, so you have this. And why you interested in this? Because, of course, you have the basic Schrödinger equation. That's the basic equation here. So they were modeling whatever. So maybe this is a condensed matter or anything. So you have some structure, and then you have a potential. And the equation for evolution of a state is a unit vector in L2. it evolves according to the Schrödinger equation. So this is the time evolution of time t of your initial state. So H is self-adjoint operator, so this is a unitary evolution that you get. Okay, so you are interested on this quantum dynamics mostly that arise from this and how it depends on the potential. Now, a lot of things are easier to explain in the case of ZT because, well, you need less quantification. There are more qualitative things that can be said. So let's discuss slightly to get easier things going on ZT case. ZT. So in this case, you have a Hilbert space that's infinite. So the space is L2 of ZT. And what kind of things would you care about? So the spectral theory of H will give information about the quantum dynamics here. So typically, for instance, one of the aspects of spectral theory of H, and then it will give you quantum dynamical properties. So let's give an example. You have the notion of a localization, which here I will simplify and discuss that localization in the case of this infinite case would be corresponds to point spectrum. So I could speak of full localization, which would mean that this operator has a basis of eigenfunctions, or could be partial localization. You could have some eigenfunctions that exist. What's the consequence of localization? So if you have full localization, for instance, then the dynamics, the quantum dynamics here is almost periodic. So it means that this orbit of the state, it stays in a compact set in L2. So that's basically immediately from the definition, you just do the spectral decomposition. So you have this full localization will give you almost periodicity of the dynamics. It's actually equivalent. All right, so that this of the quantum dynamics. And in particular, what does it mean that dynamics stays in a compact set? It means that as time goes by, my state remains concentrated, or means most of this value. Of course, is L2 is the case, but you find most of the mass of our eigenfunction concentrated in some kind of bounded region. So there will be what it means compactness. It means that for every epsilon there exists some bounded box, such that so I should start with for every u initial state, and then for every epsilon there will be an L, such that the mass exponential minus ith of u, so the gives mass 1 minus epsilon to the box, to just the box of size L, to a L-sized box. So everything remains contained and finitely many sites mostly, that my dynamics doesn't evolve this. So that is one immediate consequence, so it shows that it is. On the other hand, if you have absence of eigenvalues, this is something that if you, well, theoretically I'm a dynamicist, so this is what, if it was a dynamical systems and they were looking at the Koopman operator, you get a weak mixing dynamics. So basically, just here it should mean the exponential minus ith-hu, typically it will decorrelate with any specific site or anything that you fix. So if you look at the correlation between this, then on average, for most times, there might be exceptional times, then it actually gives very little weight to some fixed set. So here you give a lot of weight to fixed set, and in the other case, you don't give weight to fixed set. And it can be, you can go further. Of course, if you have absolute continuous spectral measures, this would correspond to, this implies mixing in dynamical systems. Here would mean that I, for instance, could get rid of this full density assumption on times. It would work for all times. So you see that the spectral theory tells you a lot of things, so this matters. I've been mostly interested just on the question of localization in this talk. All right, that's interesting. So let's give an example. So one source of operator that you can get this would be the Anderson model. So in this case, the V is sampled, V of n, that belongs to minus lambda lambda, is IID is taken independently from the uniform distribution, let us say. Okay? It's an important model, so I don't. So in this theory, it should be like you're trying to understand how a media that's here, that's disturbed by some randomness that you don't try to model exactly, just says it's random. You have a parameter that's how much disorder you put on the media, which is lambda, and you try to see what's the effect on that. And there are some theorems. For instance, one theorem that says it's just that, for instance, for d equals 1, right, and that for any lambda, so any level of disorder, the random guy, this is localized. You have full localization. Right. So this is known. And then for d bigger or equal than 2, this is known for lambda sufficiently large. Depending on the dimension, there will be full localization as well. Now, what happens to small disorder? We don't know. We don't know how to prove. Some people have expectations about that. Some people think that may depend on if d equals 2 or 3 or higher. But there are no theorems, except that in this situation, if you just assume that lambda is bigger than 0, there is partial localization. So there is some eigenvalues. It's not kind of a void of eigenvalues. So there is some part of the dynamics remains localized if you start with a state that sees it. I want emphasis. People who know that understanding exactly what happens between lambda for d bigger than 0, d bigger or equal than 2, and is a big problem. So that people that already know that, I don't need to explain, and I cannot do justice to the problem now. Anyway, so that you get all this. So you see that localization happens, and maybe it's even frequent from this point of view. It happens quite for a random set, at least partial localization anything, and then in d equals 1 always. Now, let us see what happens now if you try to understand the consequence of this for box case, because so far I focused on the infinite case. Because if I was going to talk about the box case, it kind of looks a little bit trivial because you always have eigenfunctions. You just have the spectral theory in finite dimensions, you have eigenvalues and you have eigenfunctions. I cannot do just some simple qualitative statement like this, and my space is the sphere is basically compact, so I cannot say this. So I have to make things quantitative to give sense. So now I'm going to try to say things that are related to this. So for here, I'm interested then, so in this case here, so let's assume this is a generic assumption that the spectrum is simple, right? We don't need it immediately, but whenever things are ambiguous, you can think that the spectrum should be simple. So E1 less than this, and then you have a basis of eigenfunctions. Orthonormal basis, right? Well, if the spectrum is not simple, you don't know exactly how to choose, so that's why one of the things that I'm going to sweep under the rug. But then you are given this, and then you ask, are those eigenfunctions localized or not? Well, you can think that if as n goes to infinity, you'd say that the eigenfunctions have retain some localization if they give weight to some finite piece. So you don't want the eigenfunction to kind of dissipate completely as it is. So a good measure of localization is the maximum of the eigenfunctions. The maximum is small, then it cannot give much weight to any bounded set. And this is basically equivalent on this. So I'm not asking full localization of the eigenfunction, but at least to have some thing there. So it's interesting to take the maximum as a parameter. So, but it should be convenient to look at this kind of quantity here. So things are normalized. So the 2 norm is 1, but I can work with the 4th norm. of my eigenfunction, which would be between 1 and 0, maybe bigger than 0, but and it will be close to 0 if the maximum is small, and far away from 0, so bounded away from 0, if the maximum is not too small. So this captures what I want to do. It's just formulas get better if I write this. And I'm interested in the behavior of most eigenfunctions. So to talk about localization, I'm going to talk about this quantity here. My measure of localization will be basically sum of phi j for so this kind of things, and I normalize it here to get some quantity that's between 0 and 1. And if this is close to 0, this means that most eigenfunctions will be delocalized. If it's not close to 0, there will be many eigenfunctions that have some kind of large peaks. So they do this. So this is the transition that I'm interested in. This gets a name. This depends always on the potential, so it depends, it's omega of V, which basically this, except that there was this fuzziness about simple spectrum. So actually, you need a different formula. This quantity here is better to talk about spectral measures than eigenfunctions, but it's equal when the spectrum is simple. So there is a difference. When you look at the matrix, it's easier to see, but let's not wait. So there is a quantity that is this. And this kind of theorem here, about Anderson localization, you say something about the random model, so that so it follows from, because this theorem here I stated for ZT. In practice, how people prove those theorems is by doing big box analysis and then gluing and making bigger boxes. So actually, from the proof, you already know something about big boxes. So I don't even kind of care too much at looking at the reference, but we know what it means. So this localization has an impact on big boxes, which says that after you fix a D and lambda, here it can be anything. If you take random, so you take V of n IID in the box model, so in this model here, and now n is large, you think of it large, but then you're going to have that the omega of V will tend to be bigger or equal than some epsilon, right? Bigger than 0. So it doesn't kind of become completely delocalized. There'll be a part that will remain localized from that. So there'll be many eigenfunctions, not all of them, I don't guarantee, but at least many eigenfunctions. We'll have some big peaks. Okay, so that's a consequence, and that's something that, since my title is deterministic delocalization, that's the kind of thing that I don't like for this talk. What's my goal? I look at my potentials giving me my dynamics. It happens, it was given by someone. And I imagine the following question. Suppose that I'm very careful and smart. Can I kind of change my potential, the Hamiltonian that gives the dynamic, to achieve a different kind of quantum dynamics, right? That would be my general goal. In this talk, the only thing that I want is, suppose that I'm giving anything, and maybe it's localized, it has some localization properties. Can I make a small perturbation? Can I perturb my Hamiltonian so that now it becomes delocalized, provided my space is too large, so n is large. And the theorem is true. So that's the main theorem. So the problem is that there are quantifiers. At some point, I will convince you that I know how to do quantifiers correctly. So, so probably for every epsilon, right? There are many parameters. I give those as kind of given, so that there is a dimension, and there is a lambda, right? And now there is an epsilon, right? And then for every and I will give a potential, a bounded potential. So given, so there is for every v that goes from n to the d to minus lambda lambda, I can do what I said I was going to do. There exists n0 for every n bigger or equal than n0. So this holds for every n sufficiently large, right? That depends on all those things here. Yeah, so it appeared before. Then for every v, blah, 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 there exists W also from the same space. Let's write it here. Also does the same thing, such that the omega of W is less than epsilon. So you can delocalize, and then W minus V infinity is less than epsilon. So you can make a perturbation that's uniformly small. That's the notion that I will convince you that it's a good notion, but I hope. But I can make a perturbation, just a small perturbation on each side, and achieve a reduction, a delocalization of most eigenfunctions. This quantity here governs at the same time the peak and the proportion of eigenfunctions. So that's the main theorem of this talk. Now, I should convince you that it is the correct things of quantifiers, etc. But in the hope that maybe some people already don't care anymore about my theorems, and to give them an opportunity to feel that they understand something, I tell things that they already know, right? So I'm going to need it, but you can feel good about yourself for the next moments. Because in the proof of this, there will be some, as often is the case, I have a quantitative statement, but to understand it, I need some kind of infinite statement. So from a finite statement about matrices, the easiest way to prove it will be through a statement about some infinite matrices. And the way to go from one to the other brings us to a technique that is called inspired by the Furstenberg correspondence principle. This will play a role in our proof. Right. But before doing this, so I promise you to do this, so this is key to keep your attention. But before this, let me say how I want to prove this and why I need to go to the Furstenberg correspondence principle to prove it. First, how do I see this problem? There are many things to do to get a proof. The first, to see it the correct way. And first idea is, this is an optimization problem. I have some quantity omega. I have a space that's my huge dimensional parameter space of potentials, and I want to do some local optimization and find that the value, or that the minimum of omega is small somewhere nearby. So that's my challenge. I don't know much optimization. I think that there exist methods that are based on random things and methods that are based on deterministic things. But imagine that in my space, if you look at the random place, there is localization, some localization. I feel that those are obstacles that I have to avoid if I want to minimize. So in my space, most of the place I look is actually not small, the omega. So I see that it's not quite easy to see where I want to go to do that. Because of what I would like to do, maybe use some gradient method. Looks the simplest thing that you can do, but you need to know where to point. And everywhere I look, it has some obstacles. Okay, so I have this in mind. One thing that you also put in your head is that if I have an isolated eigenvalue and I move things a little bit, everything will move smoothly around it. Isolated eigenvalues move smoothly. So the eigenfunctions will move smoothly. So I cannot do much with that eigenfunction if it's associated to an isolated eigenvalue. But I have many eigenvalues, so they cannot be all of them very isolated. So most of them need to be close together. But maybe if they're closer together, it should be easier. So imagine that you put in your head that maybe too much concentration of the eigenvalues will simplify the task of changing the eigenfunctions. With that in mind, you try to move the eigenvalues instead of moving the eigenfunctions. And you ask yourself how to do it, right? So you try to change. So I write an expression that is easy to write is something like this. So write like a formula like this. So this is a formula that gives a bounded quantity. right? Phi. Maybe it depends on V. So V defines the eigenvalues, and then you can do this. This is the alternating sum. And then this would be is bounded, but it should be actually small if you put the odd and even eigenvalues, they get too close together. Right? So that you could imagine that this being small is good for you because you're squeezing together the eigenvalues, and you have this hope that this will help make your life easier. So this kind of motivates doing things. So that, but then I want to differentiate this to see how to make it smaller. So I need to differentiate this, and then you see that it's important to compute things like this. When you change my potential at site I, it provokes a change on the potential at site j. So there is something that gives you the answer to what happens. It's called the Hellman-Feynman formula. Well, yeah. So this is just, well, I write the formula. Very simple. It's called Hellman-Feynman. Somehow when you want to see what's the effect of changing the Hamiltonian on this, you need to assume that you have some isolated eigenvalue, right? A simple eigenvalue to do this. So let's not worry about this. So that's a nice formula, some positive quantity. But then when we look at this expression, a problem arises that there will be signs. So things could cancel. Basically, it should be interesting if the derivative is big, if d phi is large, then I can really affect this by following some good direction. I can choose a good direction that makes it shrink, for instance. And you see now that it appears the question of seeing what happens, why d phi is large or small, will depend on how things cancel here. So there is one case where this is easy. So suppose that there are many phi j's with a very large maximum, very localized, so that phi j of I square is between 0 and 1, is actually bigger or equal than 1/2 plus c. So it's actually over half thing with some space to go. There is an advantage here because in this expression, if you sum over columns or over lines, this gives 1. If you sum phi j I square, it's an orthonormal matrix, the phi j's. So it cannot cancel. So this would mean that d phi, so the coefficient here would be bigger than 2c after this, because all the other coefficients have to be less than 1 minus. So this would imply that d phi would be bigger than some constant here times n, because there are n coefficients that appear, so that there are n columns and so on. So there is the n to the d, actually. And but there is some constant here. So there is a big derivative. And you see that you cannot have a big derivative together with a small function, so bounded function. So this means that you cannot have this property for a long time. As I kind of apply the gradient method, this eventually cannot work anymore, which means that I delocalize it to level 1/2. So it's easy to delocalize to level 1/2 by just doing this trick. And then you're very hopeful, but then you realize that now to really delocalize completely, you really need to understand the cancellation. This was a short, easy, and doesn't work very easily from this. There's no easy modification of this that produces a TL. Because you have to handle the localization, and you need to handle the actually the cancellations uniformly in a neighborhood. So you don't work just at the initial or something that's designed for the original potential, but you need to do the gradient method. You have to design some function that works for this. That's when you do the infinite limit. So let's go a little bit for this Fuchsenberg thing. So let's move on from this and explain what's the Fuchsenberg correspondence principle in its original application. So it's a different problem. So there is the Zemere-Dition. it looks like this. It's so you have some k, and then there exists there is an epsilon. Then there exists an n0, and then for every n large, right? So it looks similar to that. For any, so you're giving a set x contained on the interval 1 to n, right? It's big. So you have a set of large proportion in a big interval. Then there exists a plus b, a plus, and then continues, a plus k minus 1b in the set. You can find arithmetic progression of length k as long as you have a relatively dense part of a large enough set, of a big enough set. This is very well known. It's proved by, for k equals 3, that's the first non-trivial case proved by Roth, and then Zemeredi proved for 4 and then higher by combinatorial methods. Very interesting that introduced several ideas related to the decomposition of things in an orderly component and a random component, kind of random component, and this kind of ideas permeate many other things. So, but basically, imagine, let me just give one idea. In an ordered component, you think that order would help arithmetic progressions. I don't explain more. In a random component, you imagine, well, imagine that all those guys have probability epsilon of belonging to my set, and those is kind of independent events. Then you expect that this will happen with probability epsilon to the k, that you get all those things at the same time. And as long as n is sufficiently large, much bigger than epsilon to the minus k, it should happen. So that would be the role done by this. Of course, it's much more complicated than that, but you think that randomness will help you, and order looks like it should help also. Okay, so it's an interesting proof, beginning of 70s. A few years later, then Furstenberg found a different approach to this that was very, had a lot of implications, a lot of applications later, and changed a little bit the field. It connects the things to dynamics to start with. So he showed that this statement, that's quantitative statement like that one, corresponds to a kind of infinite statement about a dynamical system now, about dynamical systems. So there is a counterpart to this. And by proving the infinite statement, he gets a proof of this. You could also do vice versa, right? It actually is an equivalent, of course, to correct things, equivalent anyway, but meaning that there is a simple deduction. There is a rule, a simple rule to connect quantitative statements to infinitary statements of dynamical type, and there is a way to go from one of them. That's why you call it a principle or whatever. So this correspondence principle, what's the dynamical part? So in the dynamics, you're given what? You have a dynamical system. So this is a homeomorphism of a compact metric space. And then you're given a probability measure. I don't say everything, which is F invariant. Just have an invariant probability measure. And then you have a set of size bigger than epsilon, right? So given this, then it says that there exists, you can find A and B, so that, so what says that if there was a counterexample to this, so the principle works like this. Suppose that I have a sequence of counterexamples to this, so I can make n arbitrarily large, and I can always find a set X that doesn't work for this K, once K and epsilon are fixed. Then I can pass to the limit and get this, a set in a dynamical system that has measure bigger or equal than epsilon, and has the property that the measure of X intersected with F minus B of X, F minus K minus 1B, so this is equal to 0 for every B. Okay, so you'd get a counterexample like this. All right, so we get so there is this statement. So if this was false, but actually those two things are true, so this means that this actually, he proves this, and from proving this, he concludes that there was no sequence of counterexamples. So that's how it works. So he needs to prove this. So how does it work? I cannot give the full proof. I don't want, actually. But again, there is order and chaos. Let's look at this. So there's f from k to k, and then you look at how it acts. So there's the Koopman operator. So it acts on L2 of me. Phi goes to phi O f, right? Or psi. So you have something like this. So this Koopman operator is a unitary operator. So you're familiar because we were already talking about unitary operators. And now you do the spectral theory. Suppose that there is a basis of eigenfunctions for this, like localization. Then the dynamics is almost periodic. Almost periodic means that it's a translational compact group up to measurable things. So if it's a translational compact group, you start iterating and it goes to the identity at some point. So actually, there is B such that F minus B is just very close to identity. So all of those are basically the same set, and you get epsilon, basically. Okay, that's easy. What about if there is no eigenvalue? Well, then you get in the situation that I mentioned earlier. Those systems are called weak mixing. Actually, big part of what Furstenberg did was to actually develop the theory of weak mixing here for this purpose. But okay, it's weak mixing. Weak mixing, he showed, implies something called multiple weak mixing. That's exactly what comes here. That says that for most B, those things here behave as if the events, for most B large, those things are basically independent. So this is actually like epsilon to the k, right? So there is the almost periodic case. Sometimes it's just epsilon, and in the weak mixing case, it's sometimes it's almost all the time it's like epsilon to the k, bigger than 0. You're happy. It seems to be over. You still need to put those two things together. There is some construction. This takes some work, but you see how the decomposition in order and chaos is helping here. Anyway, I am made my. You should. This was just to make things more palatable. What happens for us? So I'm over with this, unless someone wants to hear a little bit more. What happens for us? We have a statement, which is this. It's a quantitative statement. What does it correspond in the in this situation under the Furstenberg correspondence principle? It corresponds to have a dynamical system. Same thing. But now I'm working on ZD. Somehow I need more than just one dynamical system. I have an action of ZD. So now N is, as before, it's an element of ZD. And I have a family of homomorphisms that commute. And, well, it satisfies the obvious relation. You have an invariant measure, right? Invariant probability measure by all the Cs, all the Fn. Well, and then given V is a function, continuous function, that goes to R. And now, now what do I do? I sample things by me. So I look at X sampled from me. So it's just a point on K. And I consider the random Schrödinger operator here. It's random, but it's not kind of IID. It's just random in the sense that I am sampling from a probability measure. And then for every X, I produce a potential that is a function from ZD to R, which is Vx at site n, is just small v of Fn of x. So there is this recipe that encodes into these things a measured family of Schrödinger operators. Okay, so there is this. So this is called the random Schrödinger operator, ergodic Schrödinger operator, if this was ergodic or whatever. So this is the setting. And you are interested in those guys. And you get a theorem about those guys, which is the following. So if you look at the generic, so given are f, k, me are given. And now I say that there is a dense set, or it's actually a G delta set, but let's say dense set, meaning that I can approximate anything. V from K to R. I can find the operator. Then for me, if you sample here, most every x, the Vx, the operator with potential Vx, has no eigenfunctions. So there's no more quantitative things. It's qualitative. You eliminated all eigenvalues by arbitrarily small perturbation. So this statement that became qualitative this time proves that statement. There is an argument. It's not exactly, it's not the Furstenberg. It's inspired by Furstenberg, but there is an argument that's different. But you can go from this to that. You could also go back, right? Using, you could insert a combinatorial construction into that using Holling towers or things like this. But actually, we are going to, to be true, initially we tried to prove that we thought that this would be easier, or we could put your hands, but in the end we understood that it's better to go for this. Because we are going to try to implement all the ideas that we discussed before about optimization and things like this in this infinite setting. And it will be easier because we can use techniques of measurability and things like this, and Egorov theorem, things that give you some control on objects that appear that will allow us to put our fingers on constellations. So, but for this, we are going to need a replacement for that. This Hellman-Feynman formula. It should be necessary. Let me do it here. Let's do it here. So we need to define a new formula that will allow us to work on this. The problem is that here there are no eigenvalues in principle. It certainly doesn't make sense to talk about the jth eigenvalue. So to differentiate it doesn't make much sense. So you need to have a formula that works better in this setting. And for this we introduce, there is this object that helps, which is called in this top setting, assuming that me is ergodic for this, there is an object called the integrated density of states. How does it work? You have an infinite matrix. You break it into a bounded box of size, very large size. Then you have a finite matrix, and there are eigenvalues. And you look at the position of the eigenvalues and the distribution. And you consider distributed those eigenvalues, every one with same weight. And now make the size of the approximation go to infinity, and see what it gives. It converges to a measure. And n is the distribution of this measure. So it gives the distribution of, is the cumulative distribution of eigenvalues of approximants. It's a function from R to 0, 1 that detects the spectrum. It moves up in the spectrum. It's a monotonic function. It's continuous. It's important. There is a theorem that says that this function is continuous and monotonic and so on. So that's the cumulative distribution. And with this function in hand, I cannot talk about the jth eigenvalue, but now for a real number in 0, 1 here, I can look at n minus 1 of t. This could be the real kth eigenvalue. I want to consider this. Looks reasonable, except that, well, n is not necessarily strictly monotonic. So sometimes, so the spectrum can be a counter set. This could be not well defined. It could be 2 points and so on. So it's not immediately clear that this function will be very regular. And may have issues of definition even. Well, what you do when you have this, of course, you regularize. So to do computations, you introduce a regularization, which I call the beta regularization. So introduce a function beta, continuous function from 0, 1 to R or C or something. continuous. And now I compute something that detects the, so this would be my approximation of Dirac, right? I would like to put a Dirac at T and to detect the T eigenvalue, but instead of this, I produce something that's regularized. It depends on small v, which is going to be the integral of E, so it looks at the position of the energy, and then it does this. So this is the distribution of eigenvalues. I look at so if it was as Dirac, it should be detecting exactly the T eigenvalue. Basically, that's designed to be correct. But now beta has to be a continuous function. It's not a Dirac function. So that's my function that regularizes things. And now this function is defined. And now you have a theorem. First, phi is C1. So it's a function on V. So V is an element of the Banach space of continuous functions on K. And as a function of this Banach space is a C1 function. All right. Well, I actually need a formula because it's not just qualitative things. So what's d phi? So d phi applies to a perturbation which is a continuous function as well. And you know from the Riesz representation that this should be a measure, right? So the action here is a measure, so it should be integral of w of x over k with respect to something. This something is actually absolutely continuous with respect to my probability measure, me. Of course, you want to know what's psi also. So what's psi? And now it's the part that things get good. Well, it's an integral of something. But now it sees it's the integral with respect to spectral measure of it's just spectral measure of E. Okay, it's a formula. So there is a spectral measure that you can associate. There is a choice of spectral measure associated to Dirac at 0. So there is spectral measure here, and somehow the derivative of my regularized stuff, it sees the spectral measure and takes this kind of thing. And now my goal, remember, was to get phi that was under control, not too large, and the phi that was large. Right? That was the idea because my idea is to locate a nearby almost critical point. And so I can, you want to find a minimum and you want to violate some conditions. So anyway, I need to show that psi is often large, not too small. So how to control this? Well, there are two things that you can plan and that are inspired by this. So this was an alternating sum that allowed to control that this was not too large because there were cancellations a lot here. Same thing here. Inspired by this, you write beta. So what's beta? So beta is defined on 0, 1, and you want something oscillatory. By doing something oscillatory, I make phi smaller. So remember that dn is continuous, and so n is monotonic. So this expression here will detect the oscillations and make this thing, as I put more and more oscillations, this becomes smaller and smaller. I would like to do this, keeping d phi large. So the point is that now I integrate this. And what will happen? And now is exactly what I want, because now I have atoms. The continuous part, probably it starts canceling once I do this integral. But the atoms, they may survive. So there is an atom here, and you get some value here. So there will be a sum over atoms, which could still cancel. So then there is the next idea, is localize in E, right? So there is the following idea that any atom, it has a range of dominance. You give any measure, if it has an atom, there will be an interval where the atom has most of the mass of this interval. It has 2/3 of the mass of the interval. Always exists a small interval. So an atom has a area of influence that it is dominant. That's this interval that it is given any measure. And now I benefit from the fact that I have this kind of infinite systems, that I have measurability, that I have Egorov's theorem, that I have all those nice things to make some measure theoretical statements. That so what I have to do is that I need to define some omega. So now omega of V is the thing that replaces the text the eigenvalues is something like I integral over the mi of x of the sum of the atoms. So sum E belong to R of sigma x of E squared. This plays the role of my phi. There is a fourth power, remember, on phi, that becomes a second power here when you do this. This is a countable sum. Everything is defined as it's less than or equal than 1. This plays exactly the same role as the previous omega. And this is positive if there are eigenvalues for positive measure set of x. So you look at a continuity point of omega, and you want to show that there is some semi-continuity. So this is generically continuous. And the statement is that at a continuity point, the atoms, they have to move essentially continuously. Right? When I change V, everything has to move regularly, because what can happen to an atom? It could split, or it could just disappear completely. But since there is a square here, if I do anything that's not continuating the atom, it makes the thing go down. At a continuity point, there is persistence of this. So everything tends to persist. So due to this, I can prove that if I'm not meant by contradiction, there is an argument, that there exists. So if omega is bigger than 0 at a continuity point, I can find a common interval J I can find an interval that will be interval of influence of many atoms, right? There will be many X with an atom that will dominate J, which will be interval of influence for some atom C delta Z, Z belong to J for positive measure set of X. For me, positive of X. So I can do this argument. So this is purely a measure of thing. But now what do? I use localization space. So my beta now has this interval J, and it's here that it's supported, and it does the oscillatory integral restricted to J. Now what do I get? I still get phi to go down, because the oscillatory thing is happening. But now, once I am in the good set, there will be inside J, there will be one atom that eats most of the mass. It cannot be cancelled by the rest, because it has more than 2/3 of the size, so it can, the other part has 1/3, so it remains 1/3. So for this function, so if I take this beta, what happens is the psi, so this, what means is that psi of x is bigger or equal than some delta, some constant, let's say, for measure, for me of x. Right, so you get something like this. I don't know the sign. Like there is a phase that I don't control at all. It could be, but it cannot be cancelled. So you get this estimate, which gives me the estimate that deep psi is bigger or equal than whatever c squared, right? Bigger than 0, while phi was going to 0. And all this holds in the neighborhood for all, that was all I was using this measurability, near V. All this happens near V. and this happens near V. Right? But now phi goes to 0 when you increase the oscillation. And you get a contradiction. It contradicts. It's impossible to have a derivative that's large and a function that's small in a uniform neighborhood. You just do gradient descent, and then it has to make a big change on the function. So that's the argument. I really did as much as I could of the argument. It's for people that work on this. Everything essentially that I said looks new. It's not based on techniques that were previously done, but there are ideas, but technically you can implement. What I say is that let me mention, I mentioned my student Andrea Uliana that we are working together. You immediately ask from this, can you do quantitative everything? When I did the Furstenberg correspondence principle, I kind of gave up on telling what's the relation between epsilons and n's. You can get, while Semeredi, it was possible to get, it would be awful. Then people improved that, of course. But it's useful to do the finitary statement to get a direct estimate. You need to do this translation. So we could translate the theorem. We can give a quantitative proof that n is fixed, and we just do things. So we kind of, it's very difficult to unfold this measure theoretical lemma, but we can. So many people can do it also with the Furstenberg case. We did it. We are still writing. So it's possible to do purely quantitative. There is one advantage of doing like this, which is that we can work on more things. So originally the theorem was for ZT, or graphs that approximate ZT, and it appears this object in the Furstenberg correspondence principle that's related to the fact that it was ZT. But you could consider Schrödinger operator or any kind of graph, right? It could be some finitary objects that come from somewhere that I'm interested in, and I could look at the Laplacian on this and then a potential and ask questions about this. And basically, every step of the proof goes on. So we can prove it for families of graphs of a certain kind. What's the property that's necessary? And that will depend on the graph. And there are questions that are open on this. So it's interesting to prove something about those things. So what's necessary is some property of the density of states. Basically, the continuity here. So what it means here, so suppose that you have a graph, whatever, and then there'll be some size, so there'll be n eigenvalues. So you have a potential from the graph to minus lambda lambda. So suppose that I have this. Graph is given, potential is given. Graph, you imagine that depends on some parameter n. And then there'll be n eigenvalues. Right? Let's say that size n. And then what I want is that for every epsilon that exists delta, right, such that if I is an interval of size at less than delta, right, yes, then the number of eigenvalues that belongs to I has to be less than, let's say, 1 plus epsilon n, like this. You cannot have a big, a positive proportion of your eigenvalues occupying an infinitesimally small region of energies. So this can be true, of course, for different families of graphs. To prove the continuity of this is involved the use of some harmonic analysis and basically properties of Lyapunov exponents specific for ZT. I can draw you graphs that don't have this property, connected graphs and so on. It's a property. You could think about conditions on graphs that would be random conditions or deterministic conditions that would detect this. This here has to be uniform with respect to all V. That's the thing. Mostly people study just the Laplacian and properties about the eigenvalues of the Laplacian graphs. Here I need to consider what happens when you add an arbitrary potential which remains bounded. Very well. So I think that I had 1 hour, which is now good.
Other questions? Yes.
Where do you use its Laplace operator? Can you change your Laplace
Uh,
operator?
well, you could, like, since I can consider any graph, basically you could consider higher hops, for instance. What's kind of crucial is this property. Like, let's imagine bounded interaction, because I'm talking about finite matrices. But you could put, it can be coded in this here. So large hops and a variation of the Laplace. But you need to have this property.
Any other questions? Maybe I'll ask, what's next?
There is, I'm interesting. So this actually is interesting. I decided to work now on some, this inspired some new perspective on localization. So I want to do a lot of the things that have been done to ZT from the perspective of finite box, which is very different in certain cases. In particular, I think that the perspective that's in the Anderson model is not the best. Because in a sense, what you want, like if you think that you came like in statistical mechanics, you are actually discussing about the bounded piece of your space, and you're just increasing the mesh, right? But my space is finite, and I'm interested in this space. I don't have an infinite space. And then given this, you may, but this represents like 1 meter, 1 square meter in this case. And I'm interested in looking what happens to my quantum dynamics of my electron. I have an electron there, where does it go? In traditional localization, it looks at the scale of the individual points. It looks at finite many points that capture the mass of my electron, of my position of the electron. Now, I kind of don't care if it is in the atoms, if I have a kind of perspective from far away. So I call this the perspective of the traditional localization. It's like the O of 1 scale, right? It's just bounded many atoms that capture my particle. The natural scale here would be to look at things that are concentrated on things that are small with respect to my thing. So I'd like to talk about what happens in the millimeter scale, for instance. This I care, but I don't care about the atomic scale as much. So it should be interesting to know, for instance, instead of localization is a notion, we can consider the notion of something that localizes not on finitely many points, but on a proportion that's a O, small o of, let's say, n squared, or just diameter. So the diameter of localization is less than or equal than O, small o of n. So there will be this would be the macroscopic scale. Of course, you could put some kind of other dependence here, but I think this is the big transition, growing from atomic to this macroscopic position. So, and things change. So you could conceivably be localized for the quantum dynamics at this without having actually in the situation that you traditionally call localized. And you could ask some questions about transport and so on. So that's what I'm caring about now.
I see. Thank you. Are there any more questions? Oh.
Thank you for your talk. I want to ask, what's the no eigenvalue? How to apply the no eigenvalue theorem of this to prove your main theorem? What's the
how I apply what theorem?
What's the relation between the no eigenvalue, no eigenfunction theorem?
I want to show that I destroy the spectral measures here appearing, and I want to show that spectral measures have no atoms. I'm saying that if the spectral measure have atoms, I get these contradictory estimates. So the atoms of the spectral measures, they enter into the formula in a way that avoids cancellations and makes the derivative large. So basically, if I cannot destroy completely the atoms, the derivative remains large. That's the point.
Okay, I think we should maybe let the next. We should conclude the. Okay, let's thank you.